In this video we'll be looking at an example mock paper designed from old questions focused on the topics expected in 2022's paper. So the largest topic that's expected is particle physics, which gives us a wide range of different things to look at. However, for more challenging questions, I fully expect there to be at least one 6-marker or equivalent 5 4-marker. So I've started off here with a question about interactions and particle groups, and a lot of this phrasing at the top needs to be taken into consideration as you structure your answer. So there's a lot of things being asked for, but essentially we're bringing focus on 3 different interactions and the individual named groups of particles, as are listed at the top there, for each one. Now it does also say about using examples of 2, again in bold, of the interactions you mentioned. It is possible to easily come up with more than 2 for each interaction really, but some of them are expected, some of them are beyond this level. So let's start off with the easiest interaction, which is the electromagnetic interaction. Now remember, electrostatic may have been accepted previously on mark schemes, but is far less likely to be accepted in modern papers. As such, always use electromagnetic, it's always correct. So these are going to be the charged particles that we're talking about, so when we say what's affected by them, we want to say experienced. So a force or an interaction is experienced by the particles with the property we're talking about. So in this case it's charged. So we're not referencing those 3 particle groups at the top, we're referencing the fact that they are charged. So regardless of group, the groups are more important for the other 2 interactions. So we have to state the exchange particle for each one. So in this case it is the virtual photon. You must state it is virtual. Photon alone is not enough. If you use the term boson instead of exchange particle, that is perfectly acceptable, but essentially in this point they don't really care, and boson tends to be forgotten, so they should accept exchange particle regardless. So moving on to the strong interaction, this one is specifically in its definition linked to hadrons. So we need to state hadrons. Now, as hadron is not mentioned in the top list there with baryons, mesons and leptons, I would put in brackets what a hadron is, so baryons and mesons. This way we're linking it to the start of the question, whilst also maintaining that definition of what a hadron is, a particle affected by the strong interaction. The exchange particle is fairly easy to remember here. It's the gluon, because it's holding things together in the nucleus. So, moving on, we have the weak interaction as our last one to consider. There's a fair bit more that you can say about the weak interaction, really. So we'll try and cover as much as is relevant. So we know that the weak interaction is something that's experienced by any and all particles. But rather than just saying all particles, we can define it as hadrons and leptons, because that covered all of them then. You could have listed it as baryons, mesons and leptons, same effect, but as we've defined what a hadron is previously, this is a bit shorter. Now, as for exchange particles, the 2 that they care about are the W plus and the W minus. Stating Z0 is something I'd still recommend, as it is technically an exchange particle here, but it's not required normally, because W plus and W minus will explain all of the interactions that matter. You don't actually have any example interactions using Z0 at A level. So, that summarizes all of the interactions. All we're left with needing is some examples. Now, as I've said, there are many examples you can give, and this is particularly true for the weak interaction. So, for the weak interaction, essentially any of the decays that you may have encountered throughout A-level could be used. But I always find the easiest one to use, so that you don't forget about it, is electron capture. Beta plus and beta minus have been used so frequently that electron capture is the one that's more likely to catch you off guard. Now, for the strong interaction, it's not really possible at this level to give a named interaction like this. So instead, a description is pretty much required. So we know that it is the force that binds the nucleons together. So we're binding baryons together in the nucleus. So there we're effectively using one of those key terms that they mentioned, so it ties it all together quite nicely, just in case the marks are linked to the use of that term. And finally, electromagnetic interaction is the easiest one. It's either going to be a repulsion or attraction between named charged particles. So repulsion between electrons is a really easy one, shorter to write than anything else. And there we have it. Nice and straightforward as a 6-marker goes. Do remember that that line about quality of written communication is not relevant. That is no longer assessed at A-level in physics. So instead, bullet point lists, concise structures, tables, anything you want to use as a way of expressing your information is acceptable. So this second question's quite nice, whilst also being very deceptive in some respects. You're asked to draw a labeled diagram for a particle interaction. Now, it doesn't state what type of diagram, but what it means is Feynman diagram, because that's the only real interaction diagram that you encounter. It may lead some people into thinking it should be something like the mini diagrams you do for annihilation or pair production. So, I've drawn a very simple one here, matching up with what we had for the example above for the weak interaction. Here's a case of electron capture. Solid straight lines for the particles before and after, moving upwards, so arrows showing that, the direction of time. And left to right is our exchange particle. You can usually add an arrow onto the squiggly line, but I've done a particularly bad one here, so I've added a normal arrow above it. Make sure your charge makes sense. So for this one, proton's positive charge is lost as it becomes a neutron. That means we have W plus carrying charge across, neutralizing with the electron to produce a neutral particle in the neutrino. Baryons on the left, leptons on the right. Now remember, if you're doing a decay like beta or beta minus or beta plus, I should say, then you will have your lines above that central boson. So only one particle at the start and then 3 at the end. Just make sure it's clearly positioned and nothing looks like it's going backwards in time. Again, exactly the same rules. Check your charges, check your exchange particles are present, and make sure any antiparticles have been correctly labelled and clearly labelled. In this case, the antineutrino. So a really easy and helpful question because it allows you to answer with anything, but that makes people panic and write random things that are nonsensical. Now, luckily, this question is loaded with information, so it should be relatively easy to attack, apart from the fact that many people will miss the first line or not take into account all the details. So we're told this particle K is positive, it says it as a word and as a symbol. We also have a strangeness of +1. Now the fact it gives a strangeness of +1 means you should always check your datasheet as to where strangeness comes in as a quantity. It will tell you that the presence of a strange quark makes something have a strangeness of -1. So this means we must have an anti-strange quark. We also have the list at the top of that page in the data booklet that states the names of the groups. K plus is listed there as being a meson, which you should know is a quark-antiquark pair. So that means we can immediately eliminate anything with a strange quark, as we must have an antistrange, and it must be a quark-antiquark pair, leaving us with only one option. Now moving on to the equation below, we are told K plus is decaying into 2 leptons. So lepton number conservation makes sense as a question. We've just said that K plus is a meson, so it's not in the lepton table, whereas the other two are definitely present. Be careful not to fall for the trap of looking at the charge and confusing yourself as to which one should be positive or negative here. In terms of lepton numbers, mu plus is the antiparticle, so L is -1 for that particle, whereas +1 for the neutrino. Cancels out, 0 on both sides, nice and clear. Conservation, strangeness is clearly the answer here, and if you're not sure why, K plus has a strange quark of some kind, so an anti-strange quark, whereas leptons have no quarks, so it clearly has to lose the property. This table is quite nice again, but people might have a expectation that something must be filled in every column. That's not the case. Go through it procedurally. We know that K plus is a meson, so it has to be a hadron. It's made of quarks. And we know that the other two particles are leptons, which means they can't be baryons, mesons, or hadrons. So it completes itself, really. And everything has been sequential in this question so far. It leads you through, which inevitably means we have to use the conservation laws again. So we're now told about a new equation, a new decay pathway, but this time it's not shown to us, so the first thing you should always do is write it out. So K plus turns into pi plus and an unknown x. So we should always tackle it with QBL, so our charge, baryon number, and lepton number conservations. You are not expected to do any strangeness ones, because strangeness does not have to be conserved. You should only ever do a strange conservation if you are told it is a strong interaction. So, charge is easy, because the particles have plus symbols, leaving us with 1 on each side already, 0 charge on X. Baryon numbers are 0 throughout. They're both listed as mesons, not baryons, and that means their lepton numbers are also going to be 0, because they're mesons, not leptons. Which means X is given the lovely structure here of having 0 charge, 0 baryon number, and 0 lepton number. So if baryon and lepton numbers are 0, then it must be a meson. It's the only other group it could possibly be, as we've been led throughout this whole question. We know it has 0 charge as well, so that means it has to be either K naught or pi naught, because you're not expected to know any other mesons. Unless they tell you the name of one, or the symbol of one, you're only expected to know the ones from the datasheet, which are pi and k. Now, both are accepted, but pi naught is the primary answer. K naught is in the notes as also accepted. And the reason for this is you're expecting strangeness to decay. Strangeness is usually the property that does change, the quark that does change its nature. So pi naught is the expected one because there's nothing strange about pi. There are no strange quarks present in any pion. Kaons always have a strange quark, or an anti-strange quark. So now we're looking at another niche aspect of particle physics. So again, as I've said, it's the major topic. I expect there to be 2 or 3 questions on this. So this is pair production to begin with, and this little bit about interaction with matter is very often forgotten. So it's worth reminding ourselves of the details. Now, we can easily define the idea that the photon is converted into a particle-antiparticle pair. That is the definition of pair production, and it is worth explaining that as part of the process. But because they've asked about this interaction with matter, the second mark is clearly locked behind that information. Now, what they're looking for is the conservation of a property as the reason for that interaction, and the property is momentum. So we can say that the photon interacts with a nucleus to conserve momentum. Now, it could be said to interact with an atom, but again, it's one of those things that's been refined over the years where they're expecting more precise answers, which means nucleus is definitely what they will be looking for if they ask a question like this. Our second question here is about why pair production cannot take place if the frequency of the photon is below a certain value. Now, the fact they've stated frequency rather than energy means we have a very easy first mark to tackle this with. And it's incredibly common that this occurs in these sort of questions anyway. But we need to reference the fact that something cannot happen if a value is too low. So let's redefine it in terms of energy to begin with. And all we have to do is say E equals HF to gain the first mark. So we can confirm that means, so if the frequency is below a certain value, then the energy of the photon is also going to be below, which makes it, in this case, insufficient in order to provide the energy needed to produce the particles. Now, instead of saying to produce the particles, I would recommend using the phrase rest energy, because you're not just making things, you're converting the energy of the photon into the energies of these particles. And because they're slower than the speed of light, they will gain it as mass. So it makes perfect sense, and it is tying in with a lot of that A2 knowledge that you have on energy to mass conservation. So instead of saying too low, let's just say insufficient. Any phrasing is perfectly acceptable for this, as long as you're clear in what you mean, that it is a value below the required. This is also a question that's often used for photoelectric effect when talking about photon energy versus the work function, so don't confuse it in this case. Because they've talked about frequency being below, some people might think that that is the threshold frequency, but that's not the case here. You could also use an example if you wanted to, or if they had extra marks allocated to it. For example, the basic one of an electron-positron pair needing 0.51 MeV for each particle, so a total of 1.02 MeV as a minimum for the photon. These pieces of data are again in the data booklet, they're there for that reason, just keep an eye out if they require values. Our last little question here is a very common filler one, where we have energy and momentum stated as being conserved, and they ask for two other quantities to be conserved. Now, it's worth pointing out that if they say energy, they also mean mass, because energy and mass are interlinked, as we've already had mentioned really in the previous questions. That's why it's the topic of pair production that's being used to tie with this. So we want to use something like charge, baryon number, lepton number. Any of those quantities is perfectly fine. Strangeness does not have to be conserved, and at the end of the day, mass may be on some old mark schemes, but will never be accepted again. Now, this is a classic mechanics question where they use a slightly bizarre diagram that, if you break it down, is a simple SUVAT example for projectile motion. You just have to make sure you know if it is rising or just falling. So in this, it does state that he is halfway through the jump in position A. So you know that it is just a descent that is occurring. But reading the question, it does look quite challenging because you're only given one value. Now, if we start in the classic way of writing down a vertical SUVAT for this situation, as the only value we've got is a vertical distance, we can check what we've got. So we know 1.2 meters for distance. We also know he's falling from a height that is the maximum, so u is 0 meters per second. And of course, acceleration is gravity, 9.81. So we have three values, which means we can use SUVAT equations to find either v or t. We're asked for t, so s equals ut plus a half at squared is the only option to go for. And as usual, part of it cancels out. So u being 0 means ut vanishes, leaving us with s equals a half at squared. Now I have written 0.5 at squared here, just to make it a little bit easier. That's how I tend to perceive it. Some people prefer to write 1 over 2 and then move the 2 to the other side. Entirely up to you. So if we rearrange it, we end up with s over half of a, all rooted, equals t. And if we plug in our numbers, we have 1.2 over 0.5 times 9.81, all rooted. Remember to use brackets if you're showing this, and if you're typing into your calculator. And our answer ends up as a long string of numbers, 0.4946, etc., etc. You're never expected to put a full number, remember. It's acceptable in the question, but usually a waste of space. So 3 sig figs, 2 sig figs is fine. So 0.49 in this case looks quite nice. Moving on, we then start looking at horizontal motion. Now remember that the time is carried over, because it's the same amount of time it would take for it to hit the ground, regardless of if we're talking about motion horizontally or vertically. They've still hit the ground. So we can make a note here that we're given a value for velocity of 8.5, but the most important feature is the fact that there is no air resistance. That does immediately simplify matters, but just to work through it clearly, I'm going to write a SUVAT for horizontal factors here, just to double check and make sure I haven't missed anything or nothing stands out or leaps out at me. So S is unknown, and that is what we're trying to find. Horizontal displacement, same as distance, remember. We have time of 0.49 seconds. And then we have a velocity of 8.5. Now that is stated with no air resistance, so it will be both, which makes our acceleration 0, because it's not changing between 8.5 and 8.5. So no matter what you do SUVAT-wise here, it will always simplify to a classic speed, distance, time equation. So we can say distance, or displacement I should say, is equal to Vt, which is 8.5 times 0.49, giving us an easy answer of 4.2. You can think about this logically. Is that an insane and improbable value for the situation? No, it's reasonable, as is the time. So always put it in context. They're not likely to be perfect, so they're not utterly realistic. But if you had something in the hundreds of meters, you could be worried. So for this one, we're now talking about sliding horizontally. And it gives us the distance before stopping. So we now know that there is a deceleration definitely occurring, and that the final velocity is 0. So we're needing to find the time in this case. It tells us the resistive force is constant, which immediately implies we will be finding it following this question. And reading ahead will show you do. So as that's the case, let's write down our suvat. It is simply horizontal in this case because there's no vertical change. So we have our distance of 0.35, and beyond that, we have to think carefully. We know that the final velocity is going to be 0, but we're not told in this question what the starting velocity is. However, we've previously been working with zero air resistance and travelling entirely at 8.5 meters per second. So that is our starting horizontal. It's only upon impact with the sand that there is any form of oppositional force. So V is 0, as we said, and A is unknown. It's linked to the force, unsurprisingly, which means we need to work out time using these three values. So as an equation, we want to use S equals U plus V over 2 times T. So make sure you express it nice and clearly. We want to rearrange it to find T, which is again fairly straightforward. Multiplying both sides by 2 and divide by U plus V. So we get T is equal to 2S over U plus V. So that gives us 2 times 0.35 over 8.5 plus 0. It's not necessary to put the 0, but for completion's sake, here it is. And once we plug that in, we will get an easy answer of 8.2 times 10 to the minus 2. You don't have to write the answer in standard form, but I always find it to be nice and easy to work with, rather than making a stupid error with position of the zeros and the decimal place. Easily done under the pressure of the exams. So our next question, as is easy to predict at the start, will be related to the force. So the force causing this deceleration to occur. Now, we didn't get the acceleration in the previous question, and this is worth 3 marks, so there you have it. You need to now use any equation you want to determine the acceleration with suvat. So A is V minus U over T is a nice and straightforward one to work with. So we just need to not find time. We don't need to rearrange anything. Sorry, stuck in the previous question in my head there. So let's note our time, and we can then plug in our values. So V being 0, U being 8.5 over 8.2 times 10 to the minus 2 gives us a value of 103.2 meters per second squared, and this will be a negative value. Now, the fact it's a negative value is by and large irrelevant here, because we know it's decelerating, and force will only care about direction if we didn't know it. So in this case, when we work out the force, we don't need to worry about that minus. It's neutral in terms of marks. You don't get anything or lose anything from it. So F equals ma is obviously the equation we want to use. So plugging them in, 75 times by our previous answer gives us 7,741 newtons. Now, you're not always required to put the full detail of the answer, or to put it in standard form. This looks like a fine answer to me. I do believe the mark scheme for this one had 7,700 as the answer, because they rounded it for unknown reasons. Just stick to real values. So, a nasty little question here on potential dividers. So this requires a fair bit of careful consideration, but it does at least have one nice little positive at the start, which is negligible internal resistance. So the fact we have negligible internal resistance means we can ignore any internal resistance factors, nothing fancy or clever to deal with the supply, so it should be more straightforward calculations. We do have two sets of series resistors in parallel here, so when we're asked to find the total resistance, it's going to be using the two laws for series and parallel. So just for ease of access, really, I'm going to note them here so it's easy to see what I'm doing. So for series, it's the sum of the resistances. For parallel, it's the sum of the reciprocals to give you 1 over R total. So in this case, because we've got two pairs, I think the easiest way to do it is to show it as a single equation, where 1 over RT is equal to 1 over the sum of resistances on one root. So let's make this A to E. So that means we're going to have 20 plus 20. You could write R1 plus R2 if you labelled them, but because they've got the numbers on here, we might as well just plug the numbers in straight away. So as we said, 20 plus 20. Don't just shortcut and put 40. You want to indicate where each value is coming from very specifically. And then we're going to have plus 1 over 10 plus 5. As the question states, the thermistor is 5 at this time. So you'll notice I haven't put 10 to the 3 on any of these to state that they're kiloohms, and the fact that the answer itself is in kiloohms means it's utterly unnecessary. So at this point we get 0.092, of which we need to flip our answer 1 over 0.092, find the reciprocal, and you will get our answer 10.9 kiloohms. So always double check if the unit is odd, if there's any additional factors, any prefixes. Double check, and it may save you work throughout the process. So for the next one, we have current calculation, and it is 1 mark after that 3 marker. So this is likely to be something very simple. As we've just found the total resistance in the circuit, we can just use VIR in the simplest form. So R equals V over I, as it states on the equation sheet, rearranged to I equals V over R, 12 over 10.9, and to be perfectly correct here, let's work through it properly. So 10.9 times 10 to the 3 for kiloohms. That will give us an answer of 1.1 times 10 to the minus 3 amps. So we then should obviously look at the unit given, and lo and behold, it is milliamps. So that times 10 to the minus 3 is not required in the final answer. In fact, it would cost you the mark if you wrote it. So 1.1 is what you're required to write. You could have noticed this earlier and not put in times 10 to the 3 for kiloohms because of the inverse relationship here. But doing it completely like this means at least you're guaranteeing it by showing and checking your own effects. Now, this question is one that often comes up, and it can be in multiple choice, but it always causes some difficulty. Some parts are easy, some parts are particularly harder to wrap your head around. So we're talking about using a voltmeter to measure between two positions on our diagram. So reference to the diagram is necessary. So A to C is this top left first resistor. So it's a 20 kiloohm resistor in series with another 20 kiloohm resistor. So if we plugged a voltmeter across here, what would the value be? Now, because we got 12 volt supply, that 12 volts will have to be transferred across everything in a single loop. the current would be passing through two resistors of identical resistance, meaning there would be an identical voltage across both. So 6 split in half. For the next one, D to F is our thermistor. Now, we know that the thermistor is still at 5 kiloohms, whereas the resistor next to it, the fixed resistor, is 10 kiloohms. So this gives us a ratio. Rather than it being a split in half, we've got a 2-to-1 ratio. So we have to think what the relationship is between resistance and potential difference. And we can see that they are proportional. So if we have 12 to split, then it'll be an 8-to-4 split. So nothing too complicated. Pattern recognition more than anything. Our final one is the hard one. So C to D. C to D is that weird crossover point between the two parallel pathways. And realistically, it's discussing the difference in potential across the resistors above it and below it in the diagram, at those two different phases in those pathways. There is another shortcut you can use to easily identify the value. So if we plug in some numbers here, just so that we know what we have got, imagine flowing as a current through this pathway if you added a route through V. You start with 6, you end up with 4, that gives you 10. So 2 volts is the missing value. Now this isn't a realistic thing, nothing goes through the voltmeter, remember. It's just a trick that does help you identify it. It'll either end up as a positive or negative value, but the magnitude of the value will be correct at all times. Realistically though, the difference between 6 and 8 above, and then the 6 and 4 below, is 2. So 2 volts is going to be the answer of the difference, regardless of which direction you are going. So a couple of different techniques you can use there to identify or check that sort of question. Now that leads us into part C, where we're talking now about the thermistor being heated, so the resistance changes. In this case, it's going to decrease. So we want to state and explain. So a simple yes, no, increase, decrease, that sort of thing for the state, and explain needs to realistically reference the pathway or other resistors on that pathway. Because at the end of the day, it is essentially Kirchhoff's laws that we're discussing. So, for A to C, that is our initial route through the first fixed resistor, isn't it? So, that route has 2 fixed resistors, so there's no change going to happen. Nothing at all changes there. So, the pathway that matters for the change with the thermistor is parallel to the pathway that they're asking about, so there is no effect. So the very fact that they are parallel rather than in series with each other at all immediately shows that there is no effect. So you could write it in a symbol format here as well. A to E is parallel to B to F. So there's the 2 complete pathways, but it's not necessary. Now D to F is where we are talking about the thermistor itself. So if the resistance is decreasing, we've just seen that voltage or potential difference is proportional to resistance, so we know it's already going to decrease. Now what that means in a potential divider is that any other components on that pathway, and that pathway alone, will have the inverse effect. So as V is proportional to R, we know that a greater proportion of the potential difference will now be across the other resistor. the fixed resistor with 10 kilo ohms. So that is a nice and easy explanation there of where the voltage has gone. It can't just disappear and drop out nothing. There has to be a reason, there has to be a place it's gone instead. It's been shared with. So greater proportion across that fixed resistor. And obviously this is a decrease, so let's make sure we don't miss that out. Okay, so on to question 6, and we are now dealing with further mechanics. Now, further mechanics can come up in either paper. I fully expect it to be simple harmonic motion here, simply because paper 2 is undoubtedly going to include significant amounts of circular motion in the gravitational fields section. So we start off with some basic definitions here. So conditions necessary for SHM to occur. So it's talking about the acceleration. So we've always got the acceleration towards the center or towards the equilibrium position, however you wish to phrase it. And we also have the proportionality of it, so it's proportional to the displacement. These can be described in simpler terms, but realistically they are things you need to know, so you might as well learn the tidy answers. We're then posed a situation with a child on a swing. Immediately that should conjure the image of a pendulum to you, a simple pendulum. So we can expect that to be the equation, and lo and behold, shortly afterwards we can see that a time period is stated in the question here. So we're shown that there's a time period of 3.2 seconds. So let's just highlight these key features. So we've got the swing, and we know the time period. We also have a sneaky use of a different value for g. So we're told acceleration of freefall or gravity is 9.8, not 9.81. So be careful, make sure it's clearly shown in your workings that you've used their new value, not the datasheet value, as they will be looking for it. But this is a simple pendulum equation, so it is going to be quite easy to use. T is equal to 2 pi root L over G. So if we go about this by plugging in numbers for a change, just to spice things up here, we end up with 3.2 is equal to 2 pi L over 9.8. The reason I've done this for this question is that G is clearly stated in that position in the equation on the datasheet, and now I've shown that I am using their value of G for this question without any doubt. So rearranging, we can move the 2 pi over, we can then square to get rid of the root, gives us L over 9.8, which we can then obviously move across. So 9.8 is 3.2 over 2 pi squared, and that gives us an answer of 2.54 meters. Nothing too complicated, just a potential of being slightly off if you used an incorrect value for G. Now this question is another kind entirely. This one is extremely challenging. For 2 marks in particular, this requires way too much work. So, we're told the energy of oscillation is 40 joules when the amplitude is 0.5. So that's going to be a plotting point here immediately. We know that. We're then pointed out to us that the graph goes up to 1. So it goes beyond that 0.5 all the way to 1. But we have no y-axis values to work with. We need to use the appropriate ones, which tells us that though we know 0 is 0 and 0.5 is 40, we have absolutely no idea what 1 meter is going to yield. Now, as this is a motion scenario, the energy we care about is kinetic. So let's use EK equals half mv squared. Okay. When we're dealing with this motion, it is not so simple. We have to use the idea of Vmax being equal to omega A for the amplitude, and omega being our angular velocity, because that's what's going on. We have a rotation, don't we? So omega we are given as being 2 pi f on the datasheet. That again doesn't seem like it's very useful to us, but remember, frequency is 1 over time period, which we are given, and it is something we care about and want to find out. So this is a form of the equation that will be useful to us. So if we plug everything in, we end up with a new equation for kinetic energy, a half times mass, and then in brackets 2 pi over t multiplied by A, the amplitude, and then close the bracket and square it. Obviously you could write A separately as I have, or you could have put it on the top there with the 2 pi. It makes no difference, it is the same thing. So, with that all carried out, we are going to use this equation twice. The first is to find a value for m, which is a complete unknown. Then we'll be able to plug it in to the equation with a being 1 rather than 0.5. So if we plug in these values after rearranging for m, we will end up with a mass value of 83 kilograms. So plugging it through, we will get EK being equal to a half, or 0.5, depends on how you prefer to write it, times by 83, and then in brackets we'll have our 2 pi over the time period, which is 3.2, all multiplied by 1, which is not necessary, but it's nice to show it. It shows clearly what you're doing, how you're thinking, and then you square that bracket, and that gives us an answer of 160 joules. Now this question is particularly hard if you're revising using the mark scheme, as it just states the value of 160 joules with no origin to it, so it is particularly misleading and disruptive there to your learning. But there we go, that's the process you can go through. So our top corner value ideally would be that, and lo and behold, the spacing allows for it. So we have points at 0, at 0.5, 40, and 1 being 160, providing us with a smooth curve. And that leads us into this final question on the photoelectric effect. Quantum will likely have a very specific question come up on one of the individual main focal points, energy levels or photoelectric effect. It's highly unlikely both would occur. Whichever one does, the multiple choice will usually cover the rest. So we start off with another basic definition. Again, these are very common for lots of these topics. So in this case, we're talking about the release of electrons from a metal surface when photons are incident on the surface. You could call it liberation of electrons or something like that. Doesn't hugely matter as long as you are clear in what is happening, that light is being shown on the surface, and therefore photons are hitting the surface and causing the electrons to leave that surface. The term surface is actually hugely important to get the mark, so don't just say light shining on a metal. It has to be from the surface layers that the electrons leave. They can't just leave deep within. It's just improbable to occur. So our calculation here is fairly straightforward. I doubt you'd get 3 marks for this these days. But E equals HF is HC over lambda. Plug in our numbers. The only tricky part being the fact that you're given 380 nanometers. So remember, nano is 10 to the minus 9. And that gives you an easy answer of 5.23 times 10 to the minus 19. You would always be expecting in this sort of question for the energy to be 10 to the minus 18, 19 or 20. So the fact it's in that range is nice and reassuring to begin with. Now we get slightly more required for the next one. In fact, I'd really expect those 2 marks to be swapped around. We're asked about the photoelectric effect here. Show that the photon can cause the photoelectric effect. Now, whenever we're talking about can cause it or can't cause it, we're going to be using the photoelectric effect equation to find the kinetic energy. A positive kinetic energy would mean it is possible. Negative would mean that much extra energy is required from the photon. But to begin with, we've got the work function here in electron volts, so immediately you have to convert it, or you're converting all your other values, which is needlessly confusing. So if we convert it, multiply by E, and you get your 3.7 times 10 to the minus 19 as our work function. Our equation for the photoelectric effect is HF equals the work function plus EK. Remember, HF in this case is the photon energy in its totality. So don't think you have to use H and another frequency from somewhere. It is just the energy. And if we rearrange this, to find the kinetic energy, we have HF minus work function. Makes sense. The energy of the photon, take away the amount of energy needed to release an electron, gives you the energy it'll have after. So we get a value of 1.53 times 10 to the minus 19 joules. It's blatantly obvious already before we even plug in the numbers that it was going to be a positive value. So it is a nice thing to see because we are checking that it can do it. So 1.53 times 10 to the minus 19 joules, which is proof alone, so I would usually supplement it with a comment saying yes, it is possible. You don't need much else. Our final question is testing your understanding of the actual context that we're given of the photoelectric effect. Remember, electrons leave the metal surface because the surface is negatively charged in the scenario. Excess electrons are present, so it's very easy to free those electrons from the metal surface. They're not exactly being held back at all. But if we have a positive charge on the surface, you can't remove the protons. That's not going to happen. They're bound in the nucleus. So instead, we have to be able to remove electrons against the flow of the forces here. So we would have to just state that the electrons are attracted to the positive surface. So if they did leave, they would be pulled back immediately. So the photons will have insufficient energy to liberate the electrons. You could describe this in terms that a far higher value of energy would be required to remove the electrons against the attraction of the positive charge that's been added, something along those lines. It's quite flexible as long as you get that idea that it is against the force that you're acting. Thank you for your time.